All right, in this video, we are going to be talking about 3 tests. We're going to be talking about the telescopic series test, the nth-term test, and the integral test. The first test is the telescopic series. In this case, if you have a partial fraction, I want you guys to break it apart so that we have 2 fractions. Then we are going to evaluate them at the first couple of terms. And then we're going to see that stuff will cancel out. And eventually the series will converge. And it will converge to whatever we didn't cancel out. So in this case, I have a over n plus 1 plus b over n minus 1 is equal to 1 over n minus 1. Go ahead and do your little systems of equation. Oops, that should be 1. Okay, go ahead and add to eliminate a. B is 1/2, which means that a is equal to negative 1/2. So now you have the summation from 2 to infinity of negative 1/2 n plus 1 plus 1/2 n minus 1. Now remember that even though we did partial fractions, we're not taking the integral or anything. So just leave it like this. Don't integrate. But what I am going to do is factor out the 1/2 so that it is easier for me to evaluate and plug in the first couple of terms, essentially. What I'm going to do now is, once we have the partial fraction decomposition, is plug in the first couple of terms. And then we're going to see what happens. So that's the first term. This is going to be my, well, this is term 2. This is term 3. This is term 4. This is term 5. And so forth. Now you'll start seeing that the numbers will kind of repeat itself, like this 1/3 and 1/3. And you'll know that since this is negative and this is positive, this is going to cancel out. Same thing with the 1/4, this is going to cancel out. And then same thing with the 1/5, if I were to continue on, this is going to cancel out. The pattern is going to continue. So the 1/6 is going to eventually cancel out, and then the 1/7 is going to eventually cancel out. And the only thing that hasn't been canceled is the 1/1 and the 1/2. So this is going to be the same thing as 3/2. And then I still have that 1/2 left over from my A and B that I took out, which means that this series will converge to 3/4. All right, I'm going to do the same thing for number 2. So there's that. I'm going to set up my system. So now I have a plus b is equal to 0. Negative a plus 2b is equal to 3. I use elimination. B is going to be 1. If b is 1, then a is negative 1. Which means that my summation from 2 to infinity is going to be negative 1 n plus 2 plus 1 n minus 1. And now I can find the first couple of terms starting at term number 2. So that's where I start at. That's term number 2. Term number 3. Well, this should not be 3. 2 minus 1 is 1. 3 minus 1 is 2. And so forth. You'll see that this 1/4 will cancel out with this positive 1/4. This negative 1/5 will cancel out with this 1/5. Continuing on, this 1/6 will cancel out, and then this 1/7 will cancel out, this 1/8 will cancel out. The only thing that we didn't cancel out was this 1, the 1/2, and the 1/3. If you want to keep it like this, you can. If you want to simplify it, you can. If you simplify it, it is going to be 11/6. All right, the nth term test just basically tells us that if we take the limit of the sequence and it's not 0, then your series will diverge. If the test fails, it's inconclusive, meaning that you might have to do another test that we'll eventually learn. So for number 3 here, if I were to take the limit of the sequence, n plus 1 over n, and looking at this is going to be 1. And since 1 is not 0, this tells me that my series will diverge. Looking at number 4, same process. So the limit as n approaches infinity of my little sequence. Since I have n factorial right here and n factorial up top, look at my coefficients, that's going to be 1/2. And since it's not 0, we know that it will diverge. Same thing with number 5. So the limit as n approaches infinity of n over ln of n. If I were to plug this in, this is going to be infinity and this is going to be infinity. So we are going to use our little helpful friend L'Hopital's to help us derive this. And that's going to give us 1, and then 1 over n, which is also the same thing as n. And if I were to plug that in and put it into infinity, well, that's going to be infinity. And it's not 0, which means that this is also going to be divergent. Likewise, for number 6, you're going to get 2/3. So this is going to be divergent because it's not equal to 0. Okay, the integral test. This one's the more important one out of the 3 because you have conditions that you kind of need to verify. So the integral test tells us that if we have a sequence and it's a positive sequence, and a sub n is equal to f of n, where f of n is a continuous positive decreasing function, then the series and the integral will both converge or both diverge. It's also important to note that the integral test, whenever we evaluate the integral, that number is not going to be the number in terms of my sum. That integral number here just tells me that it converges. Great. Or it has a number. Great. Which means that we know that the series will also converge. Now, we have to make sure that we know that it's continuous, positive, and decreasing in terms of these functions. If they aren't continuous, positive, and decreasing, then we'll probably have to use another test that we'll eventually have to learn. For number 7, I am going to rewrite this so that it looks like 1 over, let's see, that's 1/2, 1, so 3/2. And I'm going to rewrite that so that it is n to the negative 3/2. All right. What I'm going to do now is think about, is it continuous from 1 to infinity? Is it positive? And then is it decreasing? So for this one right here, remember to prove that a function is decreasing, we are going to take the derivative and then do a bunch of stuff with it. So I have negative 3/2 is equal to n to the negative 5/2. That is my derivative here. If I were to plug in, let's say, well, here, my critical point is just at 0. So in this case, I have 0, and then it just goes on forever. And you could see that if that's the case, then this is going to be negative forever, which works in terms of my interval right here, going from 1 to infinity, which means that since this is negative, my derivative is negative. This means that my function is a decreasing function. So we know that this is checked off. We know that it's also a continuous function from 1 to infinity. So that's checked off. And then to see that it's a positive sequence, just list up the first couple of terms or so to see what it looks like. And then you'll see that it is also positive. Once you have verified that it, aka the function, is a continuous positive decreasing function, you can take the integral from whatever your starting point is. In this case, I have 1, and then I have to infinity. And like I said, this was n to the negative 3 halves, or x to the negative 3 halves dx. This is an improper integral, so I am going to take the limit as t approaches infinity, 1 to t of this lovely thing right here. I'm going to up my power, and then I'm going to divide, so that's going to be negative 2. So now the negative 2, the limit as t approaches infinity of t to the negative 1/2 minus 1. Well, if I were to plug in infinity right here, and if I were to rewrite this, this is the same thing as saying 1 over the square root of t. And if I were to do that, 1 over some really big number is going to be 0. So this is going to be 0. So I'm left with negative 2, 0 minus 1, or 2. Now, because my integral is evaluated at 2 and it converges at 2, this tells me that the integral test, by the integral test, this tells me that my series right here converges. Now, we don't necessarily know what this converges to. It's not going to converge to 2. This was just me doing the improper integral. But this will converge. To what number? I don't know. But on an FRQ, you just want to make sure that you say that 1 over n times the square root of n is a continuous, positive, and decreasing function from 1 to infinity. Since those are your conditions, you need to make sure that you have your conditions for you to earn full credit. Just like number 8, you need to have your little condition. We're going to pretend that we checked for conditions, aka we know that it's continuous, we know that it's positive, and we know that it's a decreasing function. Given that most likely this will be in calculator inactive problem, you do have to do this by hand in terms of checking that it's continuous, positive, and decreasing. But for now, for the sake of time, I'm going to say that the function ln of x over x to the third power is a decreasing, positive, and continuous function from 2 to infinity. Therefore, the integral test may be used. And then use the integral test. So in this case, I have the limit as t approaches infinity of the integral from 2 to t. And then I have ln of x, x to the third power, dx. Now, obviously, this is going to get pretty messy pretty quickly because this right here It's the same thing as saying ln of x times x to the negative 3, which is an improper integral because you have a product. Great. Not improper. An integration by parts integral. All right, so let's go ahead and do integration by parts on the side. Up your power and divide. That's going to be negative 1/2. And then uv du, so this is going to be negative 1/2 ln of x times x to the negative 2 minus the integral of plus 1/2 and then x to the negative 3 dx. Whew, that's a lot, I know. All right, so this right here is from 2 to t. And we are going to have this. Okay. Why is my thing not working? Plus, let's see, 1/2. Up your power. Divide, so negative 1/2. And we still have my limit. All right. Evaluate this. Negative 1/2. Well, first, let me do this. Evaluate first. Let me do it right there. You might be thinking, oh my Buddha, this is really messy. Yeah, it's pretty messy. However, stuff is going to cancel out easily. Like this one right here, we have negative 1/2 ln of t times t to the negative 2. T to the negative 2 can be rewritten as this whole thing over t. Okay. So if I were to think about this right here, the natural log function grows kind of slow in terms of my hierarchy. So my linear function right here kind of beats out this natural log function because it beats out the natural log function. This tells me that because this is heavier, this limit will eventually approach 0. So this is 0. Now you have this lovely thing that we got to work out with. And then we have this lovely thing that we got to work out. This one right here, this is also the same thing as 1 over t squared, aka 0. So that's going to be done. And then you have this lovely mess right here and this lovely mess right here. But essentially, because we didn't have infinity in terms of my t right here, and we have some number, what number, I don't know, it converges. So based off of the integral test, because my integral converges to some number, what number, I don't know, this tells me that my series right here will eventually converge to some number. So this right here will eventually converge to some number. Great. All right, so now we have, let's say, number 9. very similar right here. So we are going to say that the function 1 over x squared plus 1 is a continuous, positive, decreasing function from 1 to infinity. Therefore, the integral test may be used. Oh, beautiful. Okay. All right, so we are going to integrate this, and remember that's just going to be inverse tangent. So now I have this lovely thing right here from 1 to t. All right. Now remember that inverse tangent of 1 is going to be pi over 4. And then inverse tangent of t, remember as I approach infinity right here. Oops, that's a pretty messy graph. We'll eventually approach pi over 2 because that's my asymptote. So this is going to be pi over 2 minus pi over 4, which eventually will give me pi over 4. Remember that pi over 4 does not tell me that the series converged to that number. This pi over 4 just tells me that, hey, I got an answer in terms of my integral. Because I have an answer for my integral, this tells me that my series right here will eventually converge to some number. What number? I don't know. All right, so these problems right here, 10 through 17, are mixed practice in terms of telescopic, nth-term, integral, and geometric that we learned in the previous lesson. So this is a good review.